Hi everybody, I'm Hudson. I am a software engineer at Censys. With me today is Ethan, an infrastructure engineer, and we're going to be talking a little bit about our transition from traditional SQL, so Postgres, over to a distributed database. And we've done this change as we've scaled our internet scanning pipeline to billions of results per day. So I'm going to start with a little bit of background and our use case for distributed SQL. So the core of our business is to have the most complete view of the internet. We go out, we scan assets, and we catalog and index these findings such that we're able to provide a view of what the internet looks like now and what it looks like yesterday, and so on and so forth. And so to do that, we're continuously scanning the internet, and we're also refreshing things we've seen every single day. And this gives us kind of a unique workload of continual traffic with some batch processes mixed in there as well. So to set the stage and explain why Postgres didn't cut it for our use case, let's talk a little bit about numbers. So the first problem I have up here is that our rate of ingestion is really high. We're ingesting billions of detailed internet observations per day, and this correlates to roughly 15 billion database IOPS per day. Combined with an inventory of upwards of 670 million services, there's both not enough space in one database, as well as not enough CPU in one database to make this work. And we found that we really did need to split it out horizontally to handle our load. The other problem I'm going to talk about today is the fact that we need to handle diverse APIs and read patterns. Since our data set is so large, we're unable to simply add indices if we want to query over a certain field. And we found that customers and internal applications require very different query patterns, as well as we want to be able to do internal reporting, which might add even more query patterns to this. And we've kind of solved this with some overarching architecture changes. So I'm going to step into the first problem, which is our rate of ingestion. And so as we moved away from Postgres, we knew we needed to figure out a way to scale horizontally, both with regards to more storage space and also CPU. And we ended up going with YugaByte for this use case, as it's a horizontally scalable database. It provides both a CQL query layer as well as a Postgres front end. This was really attractive for us because we knew, or we thought, we wouldn't have to change too much of our application code. I've put in this slide a silver bullet because, as we all know, there are no silver bullets in software engineering, and every approach has trade-offs. And so while YugaByte is very good at scaling out horizontally, we did have to make some application changes as we moved away. It was not as simple as just changing a JDBC URL, which, perhaps some blogs on Medium might have you understand. And I'm going to talk a little bit about some of the pitfalls that we had to overcome during our migration away from Postgres and to YugaByte. One of these is all about avoiding hotspots. On the right of my screen here, I have a little play table called event. This is supposed to represent something like an audit log where you'd want to have some time series data, and maybe store an event like a user created or a user clicked button event, something like that. And the idea here is that the application would be inserting rows with the current timestamp as the primary key. So every insert would have a timestamp directly after the other. And I'm also going to make the assumption that we want to query on that timestamp. So we want to say, show me all the events between 1 and 2 p.m. on Fridays so that we can run some internal reporting and find out what users are doing. And what happens is one tablet ends up getting the majority of your write load, where other tablet servers are not getting as much. And we found that we actually needed to introduce some application level sharding to overcome this problem. So in the second revision of the event table there, you'll see a shard ID integer column has been added. This is a application level shard that you might get from hashing the value of the event and modding that by the number of shards you have. Maybe you have 100 or 200, depending on how large your YugaByte cluster is. And what that'll do is when you write, you'll be able to spread your writes across that hash index first, and then to put it in a sorted occurred at index. And so of course, there's no free lunch. When you query, you're gonna have to query each shard individually. So at the bottom there, I've included a little example about how you might use a table that has application level sharding. You'll still be able to do your observed at range query, but you're going to have to actually query each shard individually. And so we've used the strategy sum when we need a range index on something that's monotonically increasing. Another problem that we faced is dealing with a really delete heavy workload. What can happen is if you have a query, again, on this kind of toy event table I've created, if you wanted to say, what's the first event that happened on shard 101? Looking at this query, nothing really seems off about it, but we found that it might actually time out in production, and you might not actually be able to get a result at all for it without significantly tweaking your timeout settings to allow a longer time. And the reason for this is that if you're running a delete heavy workload, those entries in the index are being marked as deleted, but of course they're not actually being physically removed. And what happens is when you're searching for the minimum event with that timestamp, it has to actually scan through all of these deleted tombstones before it gets to the first one that's not deleted. And the way that we've overcome this is by figuring out how to split a query like this up into smaller, constant size queries and run them in sequence or in parallel. The next thing I want to talk about for our migration from Postgres to YugaByte is how we've dealt with such diverse query patterns on big sets of data while retaining some of our sanity. And we've done this through something called command and query responsibility segregation, or CQRS for short. So the idea behind CQRS is that your domain model, your business logic, can be wildly different than your query model, or how customers and users actually want to interact and look at your data. And for us, this means that the pattern of our writes and the pattern of our reads are very, very different. To make an example, if we are taking in internet scan data, we might use an index on the IP address of a host. Whereas if you go to our IPv4 search data, the customer might be interested in searching over all the hosts running SSH. And we can see that these are very different patterns. And so what we found is, use the right tool for the job. And so on our right side, or the domain model, we're actually able to use the CQL front end on YugaByte and use distributed SQL on the query side. And this is really nice because it lets us run one-off reporting queries without having to change our schema or denormalize it. It's also familiar to most developers, and we're able to run one-off, we're able to spin up query-specific tables where we need it. And so if we need to index data in a specific way, we can actually just spin up a new table made for that query. So going over the architecture of a application using CQRS a little bit, you'll see at stop number 1 here, we are ingesting internet scan data through our write API. This might be something like Kafka or PubSub or even a REST API. But this data goes through the right side of our application that actually does the business logic or the domain logic. So it's modeling our domain objects, and it interacts with a database using SQL. And the reason for this is that we're mostly doing key value lookups, and we don't actually need to support diverse query patterns at this time. After it's been written to the database on the right side of the application, which we say is the source of truth, the read side of the application will read the updates and enter them into the read side of the application in a query-specific way. So for example, if we made an update to a host on the domain side of the application, the read side might put that into something like Elasticsearch, or it might put it in something like a distributed SQL database. And what's nice about this is that we don't have to run a distributed transaction on the right side of the application. It'd be really, really expensive for our system if every time we got internet scan data, if we had to both update our source of truth, our domain table, and also update the read side distributed SQL databases. So after that, a client or an internal application can query the query API of our application, and that will directly interact with the distributed SQL databases and the tables that are made to support the queries. And just to kind of sum up this talk a little bit, we found that switching from traditional SQL to distributed SQL isn't as easy as just swapping out your JDBC URL. You need to make sure you're avoiding hotspots, watching out for tombstones and expensive index scans. And really, you just want to review your SQL queries before you switch and to always be measuring your results so you know where to look if things aren't turning out the way you'd expect them. We've also found that CQRS has helped us maintain really good performance while offering a diverse query API. This is just because indices are so expensive when data is as big as ours. It also lets us use the right tool for the job, and it helps us bridge the gap between the domain model and the query model since they're so different.
Okay, thanks, Hudson. As Hudson said, my name is Ethan. I'm an infrastructure engineer at Censys. I'm going to be talking a bit about how we have actually deployed YugabyteDB to meet the challenges that Hudson has outlined from the application side at Censys. So we've actually chosen the Kubernetes deployment. We went back and forth between a Kubernetes deployment and a raw VM deployment. And I've enumerated some of the pros and cons and what led us to our choice here. The biggest cons, obviously, of the Kubernetes deployment, for those who are familiar, are stateful workloads are just, in general, a bit more challenging with Kubernetes. Its bread and butter are really stateless workloads. And when you deploy into Kubernetes, obviously, you're taking resources for the kubelet. So the Kubernetes system itself takes resources that you're paying for, that you've allocated in your VMs away from the ability, or away from usage for the database. So big pros, obviously, are scaling. Scaling of a YugaByte cluster in Kubernetes is incredibly simple. It's just changing the number of replicas for a given stateful set. And Kubernetes gives us the ability to manage a lot of the operational overhead, like DNS, some ingress, and other things like this. And the biggest influencing factor, honestly, for us is that our application workload runs in Kubernetes. And so the access patterns are crystal clear there. The application isolation was given to us innately if we chose Kubernetes. And so that was the biggest influencing factor. And so we decided to go for a Kubernetes deployment of YugabyteDB. So how did we go about doing this? We used GCP. So we've used the Google Kubernetes engine to deploy YugaByte. Our instance types are, for the most part, for our tablet servers, N1 high CPU 16s. So these are a reduced memory with respect to CPU ratios relative to a standard instance type, for instance. We've persisted our data locally on each one of these instances. So 4 local SSDs per node currently. This is a multi-availability zone, so multi-AZ deployment. We've deployed using Helm, using a modified version of the YugabyteDB Helm chart. So we've actually taken it and tweaked it for our use case. And within that chart, all of the nodes, including the masters and the tablet servers, are all modeled as stateful set objects. So in the end, with this type of deployment, with these nodes, and with the workload that we have, our current per node performance that we see is about 300 queries per second of the SQL interface, and about 1,500 queries per second of the CQ interface, which translates to roughly about 4,000 IOPS per node. And we found that this is pretty linearly scalable for us. So we run obviously more than one node, but this is translated linearly throughout. So this is just a sort of outline of how YugaByte is performing under our workload within our cluster. The top 2 graphs on the left, you see YugaByte CPU as a percentage of the limit that's reserved for it. And so we have different types of workloads, and those workloads tend to make the CPU usage oscillate essentially between about 100 and 50% of the total cluster capacity. Memory obviously stays at a fairly high rate for caching. You can see the latencies when we're at 100%. Our latencies for inserts are around 40 milliseconds on the CQL side, and this is at a rate of about 15, or total about 20K queries per second in CQL. We're simultaneously doing an SQL load on the same cluster. Our SQL load on the same cluster is around, in this particular case, when we're at about 100% utilization, we're talking more or less 5,000 to 6,000 queries per second. And we have latencies that push up during this load on the SQL side of around 100 milliseconds. This particular cluster was about 50 nodes at the time, so that should correspond essentially to that throughput and that performance that I talked about for our application workload. So I just want to spend a few minutes sort of summing up some things that we learned from an operational standpoint when we deployed YugaByte that maybe weren't, some of them were clear and some of them weren't when we started the journey. One of those things is that YugaByte has masters and tablet servers, and those have very, very, very different resource needs. Obviously, the data is stored on the tablet servers, and the masters are used more for coordination of metadata. But there are times that they don't have low resource needs. And by that, I mean that we generally have chosen, for the sake of pricing, to use a less intensive instance type for our masters than we do for our tablet servers. But there are times that we do operations, schema changes, things like this, where our master workloads actually do spike. And so we found that there are occasions where we want to change the instance type that we've used for the masters for a specific type of operation, while reverting to a smaller instance type for other operations. We also found that our SQL workloads are pretty computationally expensive versus our CQL workloads. This wasn't immediately clear to us when we started, but essentially we use approximately 4 times the CPU to do an equivalent SQL transaction with our workload than we do for a SQL query. And so as we build up what we need to do on the read side, as Hudson has referred, we need more and more and more and more resources versus the write side where we're using SQL. We've used local SSDs, and we've done this because they're cheaper and they're more performant. But when you're doing a Kubernetes deployment, one needs to be very clear that this is ephemeral storage as far as Kubernetes and GCP is concerned. So backups are critical. You can save money and you can have great performance with these, but you really have to have off-site storage, and your node pool should be as static as possible. So, and by this I mean no auto updates, no auto repairs, things like this. Anything that could actually remove a node from an automatic, unintentionally and non-deliberately from the operational standpoint should be avoided, because removing a node really means removing your data. And the YugaByte is very tolerant to single node losses, but not to, for instance, high availability or full availability zone losses and things like this. One thing we have found is that our distributed backups are a little bit difficult to self-manage. The 2 options, we have a very large data set. The 2 options for backups are essentially to do a full table scan and use the copy to syntax to move the data, which is fairly intensive on our resource usage, especially given our high data input. Snapshots are great from a resource standpoint, but snapshots require a lot of coordination to move off-site. So essentially these snapshots are stored on each node, and as you increase nodes and tablets for each given table, then the complexity increases. One thing that we found incredibly useful is that we changed our update strategy for the stateful sets from a rolling strategy to an on-delete strategy. And this has allowed us to do things like vertical scaling when necessary, to do updates in a much, much more deliberate way. On-delete allows one to update the entire spec for the stateful set and then individually delete pods and wait for the cluster to recover and rebalance before moving on to the next one. This has been critical for us. And one big learning for us is that YugaByte has a lot of metrics, and that's awesome. But sometimes the alerting patterns are less clear when something is going wrong. This is a big takeaway for us, that we had to sort of figure out, of all of those metrics, what kind of combination of metrics actually means that we're having problems. We found, for instance, things like high consensus, amounts of consensus voting followed by leader changing has often indicated for our cluster that we have issues. And those alerting patterns sort of are up to the user a little bit to discover. But despite all of these things, we've really actually found that YugaByte has been incredibly successful in meeting what Hudson described as a pretty challenging workload. And so we've been quite happy. And with that, we're available for questions. We encourage everyone to visit our website and learn more about what Censys does at Censys.io. Thank you very much.